Yeah, good afternoon everyone. The topic for our project is heterogeneous integration of silicon logic with overlaid ECZO-FET transistor based DRAM for AI accelerators. So first we will look into the outline of the project. So first we will look into the modeling of the ECZO-FET device. Then after that, we will look into the read-write functionality of the 3T0C based DRAM cell. Then we will also compare the read-write energy and latency of that particular DRAM cell. And then we will also demonstrate the logic which is underneath, where we will look into the int8 and int16 based 8x8 systolic array for the MVM computation. And then we will also also look into approximate computing, which will result in reduction in area, and also look into toroidal and bidirectional data flow for reduction in latency. And then we will show the impact of approximate computing on image compression, edge detection, and DNN inference accuracy results. So first we will look into why ECZO-FET DRAM is even needed, because normal CMOS based DRAM, they suffer from repeated refresh. This is because they have huge subthreshold leakage and gate induced drain leakage in the access transistor and as well as the capacitor. So therefore in this particular ECZO-FET device, it has very high band gap. Therefore the leakage is effectively less for this ECZO-FET device, and therefore we get enhanced retention and also massive area gains, because this ECZO-FET can be implemented at the back end of the line transistor. Now we will look into the compact modeling of the ECZO-FET device, where we have implemented a physics-based model where we have taken into account the donor occupancy of the device. Then we also look into the surface potential, which is important in order to implement the leakage current of this particular device. Then we also look into the drain current equation and also the gate charge and the short channel effects. So the graphs on the right shows the different IDVGS and IDVDS characteristics of this ECZO-FET device, and this is quite consistent with the literature that we have. So here we have compared our results with the TCAD and simulation based results, and for this particular device we observe the characteristic curve below. One interesting thing to note is that this particular device has a very low on drive current, and the threshold voltage is around 460 millivolt for this device. So even for even if you have to get substantial current to obtain the sense margin, we have to use larger sized devices. So therefore for this particular device, the size of the device will be higher compared to traditional CMOS. So here we have implemented a 3T0C based ECZO DRAM bit cell and the array. So here the storage node incorporates the weight that is stored in that capacitor, and on the plots on the right showed the read-write operations for the ECZO based DRAM cell. And then we will look into the we will look into the read-write energy and latency, and the bit cell area, as you can see, is comparatively higher than normal CMOS based DRAM, because the size of the device is higher in order to achieve substantial current to achieve higher sense margin. So here we have shown the crossbar along with the peripheral circuitry, and also the layout shows the peripheral and the crossbar area. So the task is to implement the back end of the line transistor, which we have done so far. Now we will be implementing the logic underneath. So from the table on the right, we can show that the maximum of the flops is taken by the MVM operation. So MVM is very important in this particular case. So then we will look into how we actually implement MVM. So we know that analog compute in memory, it will suffer from analog non-idealities and the IR drop in the bit line. So therefore, and also charge based analog compute in memory will have drawback because the ADC will take up a lot of area and also the power. On the other hand, digital compute in memory is very accurate, but it requires large adder trees, and therefore it reduces the memory density. So effectively it is not compute in memory, it becomes memory in compute. So since DCIM is highly accurate, we will look into digital based compute. So now we can do a comparison between digital compute in memory and systolic array based compute. We observe that DCIM consumes 22.3% lesser power than digital compute in than systolic array, and DCIM also takes lesser area than systolic array. But then why is the motivation of doing systolic array? This is because we have taken from that paper that DCIM has a bottleneck for compute bound operations. So systolic array has much lower latency compared to the digital compute in memory. So now Saptashwa will take on.
So here we present a systolic array, a normal systolic array with int 8 and int 16 precision. So each processing element looks something like this. I'll just use my laser pointer. So each processing element consists of several partial product cells, and there are two types of partial product cells, the positive and the negative ones. The negative ones just takes care of the sign bit for computation, and these are the area numbers for the int 8 and int 16 8x8 systolic arrays. Now we also have explored a approximate systolic array wherein the target was to reduce the transistor count in each of these partial product cells. Now it also depends that how much we want to approximate for each of these partial product cells. So the extent of approximation would also take a toll on the accuracy of implementation. So this is the truth table that shows the errors that we make as a result of the approximation. In case of int 8, we see a 19% area reduction, and for int 16, we see an 8% area reduction upon approximation of two of these columns in each processing element. Now, we also explored for reduction of latency at toroidal and bidirectional data flow. So we have explained it through animation the data flow for a 3x3 systolic array. And we have also synthesized it, and because of this toroidal data flow, so the buffer requirement is less, and that's why we see a reduction in area. Now this is the macro level layout wherein we have placed the approximate version and the exact version of the systolic arrays and int 8 and int 16 depending on the workload, and we do have the sense amplifiers and row decoders of the IGZO in the FEOL logic. So these are the TOPS per watt per millimeter square numbers, energy and latency for each of these implementations. And for application, we have taken three cases. First is the discrete cosine transform and the image reconstruction using an exact systolic array within 16 and int 8, and approximate version using. So here we have varied the extent of approximation, and as usual, we see a degradation in the PSNR. And the second application we have taken is an edge detection, wherein we convolve with a 3x3 Laplacian kernel, and these are the results upon approximation. And as third, we have taken the DNN inference, the impact of approximation and quantization on DNN inference accuracy for ResNet 18 CFAR 10 and for LeNet 5 fashion MNIST.
Let's stop. We are stopping everybody, okay? My question is, it seems that you have done a lot of things here, right? So, but more importantly, you're trying to show that the back end of the line IGZO with a 3T cell, DRAM cell, can be useful for DNN or whatever applications that you're looking at, right? So you implemented the systolic array in the FEOL, and the memory is on the top.
Yeah.
And so how do I compare? I see all the results. How would it compare with just FEOL? You get an increase in area, do you?
Yeah, because the entire
because you don't have any transistors coming from the back end of the line that you need in your FEOL. So that is the big advantage. Is that correct?
Yeah, right.
And in terms of performance, because these memories are not going to have as much performance as.
But as we said, that it won't also require refresh, so that would have
reduction in the latency as well, because
you need to access the memory, right?
True.
And then you have to come back.
True.
When you have to write
back to the
back to the
So do you have any analysis on that? I'm just trying to figure
as
out.
of yet.
Because we did not have the exact memory, so the back end of the line we cannot actually could not implement how we can even if you want to write it in the back end of the line device, that the parasitic drop from the FEOL to the back end of the line, those could not be incorporated.
So just to add to his answer, we had what we have not presented, but we had presented in our midterm report is we had modeled the vias for that analysis, but in the interest of time we couldn't complete it.
But you have done that.
Yeah, we have
modeled the vias from back
the
end.
result of that.
Oh, we could not integrate it with the front-end logic and these things, but the via modeling was done.
And why approximation?
Just to show the area reduction in the
Yeah.
But Wouldn't that have any impact on the performance?
Yeah, so they were having some accuracy drops as well because of the approximation.
Approximation is just on the side, is that correct?
Yeah, just to explore the drop. Yeah.
Do you have a team contribution?
Yeah.
Thank you.
Who did more work?
This is just to make sure it's a group project.
No, it seems it's a lot of work. I mean.
In my experience, I've been told it's one person has to do it. Thank you.
Thank you.